Welcome back to Mining of Massive Datasets. Today's topic is recommender systems. We're going to start with an overview of recommendation systems and why they are necessary. Then we're going to look at the two most common types of recommender systems, content-based systems and collaborative filtering. And finally, we're going to look at how to evaluate recommender systems to make sure they're doing a good job. Let's start with an overview. Imagine any situation where a user interacts with a really large catalog of items. Now, these items could be products at Amazon, they could be movies at Netflix, they could be music from Pandora's catalog, or they could be news items on Google News. What really matters is that there are tens of thousands or hundreds of thousands or millions of items, a really large catalog, and the user is interacting with this catalog. Now, there's two ways in which a user can interact with a large catalog of items. The first is search. The user knows what they're looking for, and they go and they search the catalog for the precise item that they're looking for. Now, when you have a really large catalog of items, very often the user doesn't know exactly what they're looking for, and this is where recommendations come in. The system recommends to the user certain items that they think the user will be interested in based on what they know about the user. Now, why do we really need such recommendations? The key that made recommendations so important and why recommendation system developed so much in the last 10 or 20 years is that we moved from an era of scarcity to an era of abundance. What do I mean by this? Imagine that you were out shopping 20 years ago, and you'd go to a local retailer and you'll find a certain number of products on the shelves of the local retailer. Now, even in a really large retailer, like a Walmart, for instance, shelf space is a scarce commodity. It limits the number of items that the retailer can carry. Shelf space is expensive because it involves real estate costs, and therefore a retailer can carry only a certain number of products. Now, a similar situation applies in the case, for example, of TV networks. A TV network can carry only so many shows because there's only so many number of hours in a day. And there are only so many movie theaters, so they can only screen a certain number of movies. Now, once the internet was developed, things changed. The web enables zero-cost dissemination of information about products. And what this means is that we can have many more products than ever before. There is no shelf space limitation on the number of products. That's why the number of products on Amazon is much, much more than the number of products available at any physical retailer. The number of movies available on Netflix is more than the number of movies that were ever available at a Blockbuster, and so on. This near zero-cost dissemination of information gives rise to a phenomenon that's called the long-tail phenomenon. Let's examine what this is. Now, imagine a graph where on the x-axis, we've taken the items in the catalog. Remember, items might be books or music or video or news articles. And we've ranked these items by popularity. So the most popular items are on the left, and as we move towards the right, the items become less and less popular. What do I mean by popular? Well, I mean the number of times the item is purchased in a week, or it could be the number of times a movie is viewed in a week or a month or some fixed time period. Now on the y-axis, we have the actual popularity, which in this case I've shown as number of purchases per week. It could be number of views per week, or it could be number of plays per month for music and so on. So in general, you have items ranked by popularity along the x-axis and the popularity itself along the y-axis. Now when you take items in a large catalog and you rank them and you plot them on this curve, you get a curve that looks like this. You can see that this curve, has a very steep fall initially. You have a few really popular items, and then as you move towards the right, as the item rank becomes greater, the popularity falls off very steeply. But at a certain point, you can see that this popularity stops, falls off less and less steeply, and it never quite reaches the x-axis. The interesting thing here is that there is a cutoff point. Items that are less popular than this cutoff point, might be purchased perhaps just once a week or maybe once a month. If you're a physical retailer like a Walmart, it's not economic to stock this item because the rent cost of stocking the item is more than you make when you sell the item. And therefore, a retailer, any right-thinking retailer, doesn't stock items that are unpopular. They only stock the head of this distribution. So there's this cutoff point that I show on this graph here, and items that are more popular than this, the more popular items, are available at a retail store. But the less popular items, the items that are to the right of the cutoff point, are not available at any retail store. They're only available online. Now, this phenomenon applies to books, to music, to videos, to news articles. For example, there are only so many news articles in a newspaper, but when you go online, you can see the rest of the news articles, the less popular news articles that are off to the right. The piece of the curve that is to the piece of the curve here that is to the right of this dividing line is called the long tail. These are the items that are available only online. The interesting thing is this area under the curve here. And you can see the area under the curve here is quite significant. In fact, in some cases, the area under the curve on the right is about as large or could be even larger than the area of the curve under the curve on the left. So you have all these items that could never be found in a physical store, but that can be only found online. But there are so many of them that it's very hard for any user to find all these items. Right? So when you have this era of abundance and you have so many items, and many of them are only found online, how do you introduce a user to all these new items that they may not otherwise find? When you have more choice like this, when you have these millions and millions of items that are only available online, you need a better way for the user to find all these items. The user doesn't even know where to start looking, and that's where recommendations engines come in. So recommendation engines work in the case of many, many kinds of items: books, music, movies, news articles. Interestingly, they even work in the case of people. For example, when you go to Facebook or LinkedIn or Twitter, there are so many people that you don't know who to follow or who to friend. And so Facebook or LinkedIn or Twitter makes recommendations to you on the people that you could follow or friend. I'll end this point with an interesting anecdote that shows you the power of recommendation engines. Several years ago, a book was published called Touching the Void. It's a book about mountaineering. It's a very, very good book. The book came out. It didn't make much of a ripple. A few people bought the book. It got some decent reviews, but it never became a bestseller. And then a few years after Touching the Void, a new book was published on mountaineering called Into Thin Air. Now, Into Thin Air picked up traction, and lots of people started buying Into Thin Air. Amazon noticed that a few of the people who bought Into Thin Air had also bought Touching the Void. So they started recommending Touching the Void to people who bought Into Thin Air. And lo and behold, those people started buying Touching the Void as well. The interesting point is, this made Touching the Void a bestseller. In fact, it became a bigger bestseller even than Into Thin Air, even though a few years ago it had sank without a trace. So this example should show you the power of recommendation systems. There are these items, these sort of gems like Touching the Void, that people don't know because they don't know to look for them. But a good recommendation system can expose people to these hidden gems that they wouldn't have known about otherwise. So let's look at types of recommendation systems. The simplest and the oldest kind of recommendation is editorial or hand-curated. You might find a list of favorites. For example, when you go into your favorite neighborhood bookstore, you might find staff picks. Certain books are marked off as staff picks, right? And these are editorial or hand-curated. And on certain websites, you'll see a list of staff favorites, or you'll see a list of essential items. These are essentially built by hand. And another place where you'll see these editorial recommendations is often on the home pages of websites. For example, if you go to the home page of most popular websites, including product websites, you'll see editorial picks. These are products that have been picked by the editorial staff to feature on the home page. The drawback with editorial or hand-curated recommendations is that it's done entirely by the staff of the website, and there's no input from the users of the site. So when you go beyond editorial recommendations, the next simple thing that you can do is simple aggregates. On many websites, you'll see lists of top 10 or most popular or most recent. For example, if you go to YouTube, you can see the most popular videos, for instance, right? So these are simple aggregates which sort of take into account user activity to make recommendations to other users. But these recommendations don't depend on the user. They only depend on the aggregate activity of a lot of other users. The third and most interesting kind of recommendation to us is recommendations that are tailored to individual users. Right? For example, book recommendations tailored to your tastes, or movie recommendation based on the movies that you watched previously, or music recommendation based on your music interests. And this is our focus here, recommendations that are tailored to individual users. So let's look at a formal model. Let C be a set of customers and S a set of items. We're going to create a function called a utility function or a utility matrix. The utility function is a function that looks at every pair of customer and item and maps it to a rating. Okay? R in this case is a set of ratings, and for example, R could be a star rating from 1 star to 5 star, or R could be a number between 0 and 10. In general, R is a totally ordered set, so that a lower value indicates that the user liked the product less, and a higher value indicates that the user liked the product more. Okay. Let's look at an example of a utility matrix. Now on the top we have 4 movies here, Avatar, Lord of the Rings, Matrix, and Pirates of the Caribbean. And down here we have 4 users, Alice, Bob, Carol, and David. And the utility matrix gives you ratings for certain movies and certain users. For example, Alice has rated Avatar and Matrix, but not Lord of the Rings or Pirates of the Caribbean. Whereas Carol has rated, the same 2 movies. Bob has rated Lord of the Rings and Pirates, but hasn't rated Avatar, or Matrix. Now, it could be that these users have not seen these movies, or it could be that they've seen the movies but not bothered to rate them. So, in general, a utility matrix like this is going to be sparse. Most of the users haven't seen most of the movies, and there are going to be values in some of the locations. The key problem in recommendation systems is to figure out these unknown values. For example, you've seen that Alice has rated Avatar and Matrix, but hasn't rated Lord of the Rings. So the question is, can we figure out what Alice's rating for Lord of the Rings will be based on her other ratings? Can we figure out whether she'd like Pirates or not? Right? So this is the key problem for recommender systems. Once we find out for each user certain movies that they would have rated highly, or which the system thinks they might have rated highly, then we can recommend those movies to those users. So there are 3 key problems in the space of recommender systems. The first is gathering the known ratings in the matrix. Now in the previous slide, when you looked at the utility matrix, it was already filled in with certain values. But how do you gather those values in the first place? So that's the key, that's the first problem that you need to tackle. The second problem is to extrapolate unknown ratings from known ratings. But we're mainly interested in the high unknown ratings. We're interested in those ratings where a user would have given a high rating to a movie. We're not interested in the average or the low ratings because we're never going to recommend those movies to the user. And finally, the third key problem is evaluating extrapolation methods. Once you have a recommendation system that can extrapolate unknown ratings from known ratings, how do you know that the recommender system is doing well? This is where the evaluation methodologies come in. Let's start with the first problem, that of gathering ratings. The first and simplest way of gathering ratings is what I'll call the explicit method. Simply ask people to rate items. Now this method is good because you're asking people to directly rate items, and you're going to get and you can decide on what scale people are going to rate items. For example, you can ask for ratings on a 1 to 5 star scale, or you can ask people to rate on a scale from 0 to 10, or you can just ask people to say whether they liked an item or did not like it. So the explicit method has the advantage of simplicity and of getting direct responses from users. The problem, though, is that it doesn't scale. Only a small fraction of users who viewed a movie or listened to a piece of music or bought a product actually bother to leave a rating or review. Most users don't actually leave ratings or reviews. So while the data that's explicitly gathered is excellent data, it's not sufficient in most cases for recommendations because only a small fraction of users actually leave ratings and reviews. Since explicit ratings don't scale, a lot of sites use implicit ratings. Now, the idea behind implicit ratings is to learn ratings from other user actions. For example, an online shopping website might have a rule that a purchase implies a high rating. Now, the nice thing about implicit ratings is that they're much more scalable than explicit ratings, because the user doesn't have to explicitly rate an item, and there are way more other actions such as purchases than there are ratings. The problem, though, is that it's very hard using implicit ratings to learn low ratings. It's quite easy to learn high ratings because you might have a rule that a purchase implies a high rating, but you can never learn a rating that a user disliked a product implicitly. In practice, most recommender systems and most websites use a combination of explicit and implicit ratings. Where explicit ratings are available, they use them, but they supplement them with implicit ratings when needed. Let's move on now to the central problem of extrapolating utilities or extrapolating unknown utilities from known utility values. The key or central problem that we have to surmount to extrapolate utilities is that the matrix U, the utility matrix, is very, very sparse. Most people have not rated most items, and this introduces a slew of problems that we'll come across shortly. The second problem we have is a cold start problem. When you have a new item or a new user, the new item doesn't have any ratings, and new users have no history. So this is known as the cold start problem, and we'll have to tackle this problem as well in due course. There are three approaches to building recommendation systems. The first is content-based recommendations. The second is collaborative filtering. And the third is latent factor-based models. Let's start with content-based approaches.